Alrighty, welcome back. Honor students, this little introduction is going to be a repeat for you, so go ahead and just skip about 30 seconds into the video. General chemistry students, today we're going to be talking about temperature and heat and how heat is transferred and how this affects particles as well. So temperature is a measure of how hot or cold something is. Specifically, it's the measure of the kinetic energy in something, and kinetic energy is just how fast particles move that causes the energy in them. And that's how we feel it. We feel it as something being hotter or something being colder. Many people often confuse temperature and heat. Heat is specifically the measure of transfer of energy between two things due to the temperature difference between them. So it's the energy transferred between two objects because of how hot or cold they are. So if something's hot over here and cold over here, heat would transfer from off of the hot object and be absorbed by the cooler object because of the temperature difference. As always, if I'm going too fast, make sure you pause the video to get your definitions down. To continue, you probably learned about this in the past, but there's three different types of heat and energy transfer: conduction, convection, and radiation. We're going to talk about each one of those today. Conduction is the direct transfer by contact. Okay, the direct transfer of heat because two things are touching. So when you're cooking something on a stove, your pot heats up because it's touching the metal of the hot stove. Okay, if you touch a pan that comes out of the oven, you get burned because you touched the hot pan and the heat transfers from the pan to your hand and burns you. Whereas convection is heat transferred through a liquid, which is caused by motion. So if you have a pan of water, the water gets hot because the liquid molecules are heating up and moving, and they're heating the other ones around them. Okay. You can also use convection not necessarily through a liquid, but through air. So you're cooling yourself using a fan. Whereas radiation is the movement of heat waves. So a fire gives off radiation through heat waves. You're feeling the heat, or you're cooking over a campfire. You're cooking your things through the heat radiation of the fire. And this little picture just shows that conduction is directly touching the pan. Convection is going on inside the water in the pan, and radiation is being given off around the pan to the surrounding environment. Three other methods of energy storage. Let me go ahead and fix this really quick so they don't all pop up at once. Alrighty, sorry about that. So, three methods of energy storage. The first is thermal. So thermal energy is the amount of energy a system has based on the motion of the particles. So thermal energy is the same as temperature. Okay, so the temperature is what we feel or sense when we touch something, so how hot or cold something is. Whereas thermal energy is the amount of energy something has based on how fast the particles are moving, which causes its temperature. Another type of energy storage is phase energy storage, which is potential energy based on how close two objects are to each other. So the closer they are, the less energy that's involved. Okay? What that basically means is when things are really close together, they can't move very fast, okay? So they don't have a lot of potential energy. Whereas in a gas, if something's really far apart, particles can move all over. So they have a lot of potential energy. They have potential to move all over and increase their amount of energy. And then there's chemical energy. We generally won't use a lot of chemical energy, especially in this unit, but it's just the energy that's stored in chemical bonds. And we'll talk about that more when we talk about breaking bonds and forming bonds and how to do that in the later units. But we talked about compounds and how compounds are bonded together with chemical bonds. In those chemical bonds is chemical energy, and it takes energy to make and break those bonds. And breaking bonds and making bonds absorbs and breaks energy all over the place. Sorry, that was confusing how I wrote that. But when bonds form, energy is released. When bonds break, it takes energy. And again, we'll talk about that more in the future. So don't worry about that right now. Just know that chemical energy is a thing, and energy can be stored in the form of chemical bonds. So we talked about the law of conservation of mass, and we determined that mass cannot be created or destroyed. Energy can also not be created or destroyed. It can only be transferred, okay? You can never make energy. If you lose energy, it goes to the surrounding system, and one other system will bring it in. If you make energy, you took it from the surrounding system. You didn't make it out of nothing, okay? And the system is that the object area of focus. So the system is what we're specifically looking at, whereas the surroundings is everything else. Okay, so if I'm trying to calculate the amount of energy released when I put Alka-Seltzer in a bottle of water, the system is the Alka-Seltzer in the water and whatever it's contained inside. Whereas the surroundings is everything else around me that I'm not paying attention to. I'm only paying attention to the energy in the bottle and the Alka-Seltzer tablet, not everything else. A couple more things for you to think about is exothermic and endothermic. In class last week, we did a pretty cool demonstration on exothermic and endothermic reactions, so I'm sorry you missed out on that. But you've probably heard of these terms before, okay? So thinking of hand warmers and ice packs. Endothermic and exo are ways to tell where energy is going, okay? So it basically is something feeling hot or is something feeling cold, and it'll tell you which way an energy is flowing. Okay? If the system loses energy, it's an exothermic reaction. So if it's feeling hot, it means that energy is going out. Okay? So if something feels hot, it's because it's emitting energy. So you feel that. Okay? It's warm. The system loses energy and it gets hot. So it's exothermic because energy is exiting the system. Whereas if the system gains energy, it's going to bring it in, endo and in. It's bringing energy in, which makes it feel colder, okay? It's taking energy away from the surroundings. It's making it feel cool. And lastly, let's talk about phase changes, which you've also probably talked about before. Hopefully, if I can find an online version, you will be having an activity on phase changes online. So fingers crossed I find something. A phase change is just whenever a change of state occurs by heat loss or gain. So if you have an ice cube, it melts from a ice cube to water, and then it evaporates to gas. Or it goes from gas and it condenses into water and then freezes back into the ice cube. The temperature is not changing during the process of changing. We know that eventually, yes, the ice cube is getting colder, but the process of going from freezing to melting, the actual phase change, there's no temperature change. It's happening in between the phase changes. And that'll make more sense when I show you this phase change diagram in a moment. Okay, so you're probably wondering, where does the energy go and where was it deposited? Okay, so this is a phase change diagram. As you can see, we have temperature mapped over on the side, and if my little thing will go away, you can see that energy is on the bottom. And as we go to the right, energy increases, and as we go up, temperature increases. So these are broken into separate segments. Okay, we have a lower portion and an upper portion. We're going to explain each of those portions. So you can see that we're going to always start with a solid. If we're thinking of ice, things are different for heating and cooling curves, but we're looking at a heating curve, okay? So we're starting with ice, and you know that in ice, from our Change You Can Believe in activity, that ice is a solid, and it's really tightly packed. So as you can see in our little ball here, everything is really tightly packed. As you can see here, our temperature stops here. Wait, stop. Okay, our temperature stops here. We're not increasing temperature anymore. We have a little bit of a plateau. As we plateau, we're changing from a solid to a liquid. This is our phase change. We're going from a solid to a liquid because the particles are able to move a little bit. They're gaining energy. Once it's in liquid phase, we're able to heat up again. Okay, once we heat up again, you can see that things are moving faster. So we can't go right from solid to liquid to gas. It takes a little bit of energy and a temperature increase to get to where we need to go. So now we have the molecules moving even faster, and once they get to a certain threshold, they're able to convert into another phase change and evaporate into a gas. And then from there, as they continue to get hotter, they'll continue to be a gas and stay a gas. Okay, so notice that temperature change is only happening in between phase changes. Again, I'm going to hopefully have an activity for you on this. Let me know if you have any questions on any of these notes. Thank you.